Hey everyone, welcome to Physics 40S. This is Unit 3, Lecture 3. We're still talking about forces. Today we're going to focus on the inclined plane. So let me get, here we go, Unit 3, Lecture 3. Real-life situations occur often on ramps, hills, or other forms of incline. Inclined plane problems are very common. You're going to use coordinate rotation. You're going to rotate the coordinate system. Choosing a convenient coordinate system is something important in physics. So we're going to use axes that are parallel and perpendicular to the incline itself. So I'm reading from the mini text. I'm also going to be using the booklet that we have around page 21 on inclined planes. So let's say we have a girl sitting atop of a frictionless snow-covered hill on her inner tube. If the hill is inclined at 25 degrees to the horizontal, so my theta is 25 degrees, that's what we define as our angle. What will be the girl's acceleration due to gravity? Okay, so the girl is going to slide down the super slippery hill, I guess, if there's no friction. What's going to be her acceleration? So this drawing in the mini text is better than the drawing in the booklet, I think. Here's the girl, and we have gravity going down towards the center of the Earth. Wherever she is, it's going down towards the center. But what we're going to do is we're going to resolve that gravitational vector into a perpendicular to the inclined plane surface and parallel to the inclined plane surface component. That will help us to solve the problem. Okay? Assuming that the girl doesn't fly up into the air or get driven down into the plane, the normal force and the perpendicular force are going to be the same. So not all of gravity, just the parallel component to the incline will cause the acceleration. This is my symbol for parallel, my symbol for perpendicular. And the math shows it's similar triangles, that theta 1 to 25 degrees is the same as theta 2. If you just flip this triangle over, you'll see there's similar triangles, so theta 1 equals theta 2. And if this is my right angle triangle, then this angle here is going to be force of gravity is my hypotenuse, so mg cos theta, and then my F parallel is mg sine theta. Oh, we have it written up there. So another way, if you don't want to keep redoing similar triangles all the time, is just, I like it like this. F parallel is mg sine theta because you're sliding down the slippery slope. So that's my parallel component of gravity. And my perpendicular component then is the other trigonometric function we've been using. Well, we'll be using tangent, but cosine. So F perpendicular is mg cos theta. Sometimes you see it written as FG parallel and FG perpendicular, but that's too many subscripts. So just F parallel and F perpendicular are good ways to write it. And so in this case, F, the normal force, equals the perpendicular force, equals mg cos theta. If we had friction, force of friction would be mu mg cos theta. We don't have friction in this example, but we will in other ones. So then my net acceleration down the ramp, well, Newton's second law is the net acceleration is F equals ma. And so it's going to be F parallel, which is mg sine theta. So you see that the mass of the girl is irrelevant in this idealized sense. It cancels out. So the acceleration down the ramp is just a g sine theta. We assume we're at the surface of the Earth, so 9.8 sine of 25 degrees. And punching that out, 9.8 times 25 sine, we get 4.14 meters per second squared. Okay, the acceleration down the slope, 4.14 meters per second squared. It doesn't matter what the mass is. If I'm making the angle greater, let's say 90 degrees, the sine of 90 is almost 1, and the acceleration would be 9.8 times almost 1, which is 9.8. So you'd get a much greater acceleration if you're at a much steeper incline. And if your incline is 90 degrees, well then you're going to be falling at 9.8 meters per second squared. If you're no incline, then there's no acceleration, right? Sine of 0 is 0, so 9.8 times 0 is 0. It's always good to look at those limits, 0, 90, and here we're somewhere in between. This whole example there, I just talked about. If I go, let's see, unit 1. Okay, well now before I do the next one, let's just looking at the inclined planes here. I'm putting in friction. I'm putting in a possible applied force, and so this is a more general case than the one I just looked at. F perpendicular is Fg cos theta, which is mg cos theta. F parallel is Fg sine theta, which is mg sine theta, so that's all good. The normal force and the perpendicular force are equal. Force of friction is mu times the normal force, so mu Fg cos theta, and Fg is mg, so force of friction is mu mg cosine theta. The net force, if you're going down, will be the applied force plus the gravitational force minus the friction, and that would equal ma. Okay, so we're going to see that in our second example. So here we have an inclined plane problem which has friction. So we have Evel Knievel driving his motorcycle up a ramp. He's a daredevil, inclined at 30 degrees to the horizontal before jumping over a row of cars. If there's a constant frictional force of 1,000 newtons on the ramp, so friction is opposing the acceleration up the ramp, determine the force that the motorcycle engine must apply to accelerate the motorcycle up the ramp at a third g. Sometimes acceleration is written as multiples of g or fractions of g. So as soon as you see a third g, let's change that to a number meters per second squared. So 9.8 divided by 3 is 3.27 meters per second squared. And the combined mass, and we're going to need this, of Evel and the motorcycle is 250 kilograms. So here's a great picture of what's going on. The engine force, that is my applied force of the engine. I got the normal force and the perpendicular force. They're going to cancel out because, again, we don't want the motorcycle to fly into the air or get driven into the ground. So perpendicular and F normal are the same. Friction opposes the applied force, and then gravity we're going to break down into the two components, F perpendicular and then F parallel. So this time you're fighting gravity, right? So assuming up the ramp is positive, fine. My net force is going to equal ma, so it's going to be the engine going up plus parallel. You're going to say, no, parallel is going opposite. But that's just, here we're just writing a vector equation, right? This is just a vector equation. Now let's take direction into account. So engines going up, applied force, and then parallel and friction are going down. So F engine minus F parallel minus F friction equals ma. So F engine equals ma plus friction plus F parallel. F parallel we know is mg sine theta. Here's theta is 30 degrees. Force of friction we know is 1,000. So we can get going up the ramp, the applied force is going to be m times a. So 250 times the acceleration up the ramp, 3.27, plus 250 times g, g is 9.8, times sine 30 degrees. Notice we got two accelerations here, right? Acceleration up the ramp and the acceleration due to gravity. Acceleration up the ramp, I use lowercase letter a. Acceleration due to gravity, I use g. So 250 times 3.27 plus 250 times 9.8 times sine of 30. And then I do that plus 1,000. So I get 3.04 by 10 to the 3 newtons. So that's the applied force of the motorcycle engine to go up at 3.27 meters per second squared. Now let's do a bit more here. Let's get the coefficient of friction, because I know the normal force is the same as the F perpendicular, so it's mg cos theta, so 250 times 9.8, 250 times 9.8 times the cosine of 30 degrees. Let's punch that out. 250 times 9.8 times 30 cosine, and I get 2121.76. So that's my normal force. And remember that friction is fun. Force of friction is mu times the normal force. So mu is the force of friction over the normal force, which is, force of friction was given 1,000. The normal force is 2121.76. So 1,000 divided by 2121.76 is 0.47. So that is the force of friction. Sorry, that is the coefficient of friction, 0.47. And that's going to be important as you're going up a ramp. I remember reading a story where a daredevil motorcycle stunt was being done outside in a Las Vegas parking lot, and everything was set up the night before, and then there was a very slight amount of rain, and it changed the coefficient of friction, and the motorcyclist got hurt because the measurements were now off because the coefficient of friction had changed. Here I'm just going to the booklet and making sure, yeah, 0.47, so that all works. Okay, let's try a few of these examples together. We won't try all of them, but let's try a few here. On page 196, we have a copy of some textbook, leaving the printing press and slides down a 4-meter ramp. So the distance is 4 meters. There's the ground. There's the book has been just dropped down, not thrown down. And there's an eager physics student at the bottom here. If the ramp is inclined at an angle of 25 degrees, so here's my angle of incline to the horizontal, and has a coefficient of kinetic friction of 0.1, so mu equals 0.1, how long will it take the 2-kilogram textbook to reach the student? Okay, so rather than reinventing the wheel, let's just think what's happening here. We're having a normal force, we're having force perpendicular, we're having force parallel, we're having force of friction. We don't have a rope or anything to pull it down, it's just force parallel, which is helping it go down, and force of friction is going against it. So if I go and look at the example here I have the worked out examples. So my force of friction is mu times the force normal. You don't have to put mu k, you can if you want. The normal force is mg cos theta, so the textbook was 2 kilograms. Acceleration is 9.8. Angle of inclination is 9.8, is at 25 degrees. So 2 times 9.8 times cosine of 25 is 17.76 newtons. The force of friction is mu times the normal force, so 1.776, or round off fine, 1.78 newtons. And then the net force, which equals ma, is the parallel minus the friction. So the parallel component is mg sine theta, so 2 times 9.8 times sine 25, which is 8.28, minus 1.78. What's that? What's the 1.78? Oh, that's friction, right. So my net force going down the ramp is 6.5 newtons. The acceleration going down the ramp is the net force over the mass, 6.5 over 2, 3.25 meters per second squared. Let's fix that, so it's squared. Okay, so all of that stuff with the cosines and sines and everything was allowing us to get the acceleration down the ramp. So displacement, or just the distance traveled down the ramp, that's good enough, is 4 meters. We are, really V1 is 0? I don't think so. V2, that's not a 2, that's a 1. V1 is 0, right? We're going to assume, because we aren't told otherwise, that it's just dropped onto the ramp. It's not flung down the ramp. Acceleration 3.25. Delta d is v1 delta t plus 1/2 a delta t squared. So the v1 delta t vanishes. Solve for delta t, and you get 1.6 seconds. Was that the question? Did it ask how long it takes till you get it? How long will it take to take the 2 kilogram textbook to reach the student? Okay, so it takes 1.6 seconds. If I wanted to find the velocity there, I could do velocity final. v2 is v1, which is 0. 2 equals v1 plus a delta t. The acceleration down the ramp, 3.25 times 1.6. So 3.25 times 1.6 is going to be 5.2 meters per second. So that's the speed at the bottom of the ramp. And the physics person has to be strong enough to catch that. Okay? If you have questions at number 1, please email them to me. Let's look at example 2. Plastic case from your least favorite CD recording, remember CDs, is flung up a frictionless ramp, inclining at an angle of 20 degrees to the horizontal. If the case leaves your hand at a speed of 4 meters per second, how long will it take before the case comes to rest? So my V1 is 4 meters per second, my V2 is 0 meters per second, my theta is 20 degrees. So here I have a ramp, and I'm throwing something. So I'm giving a speed up the ramp, okay? And it's frictionless, so I don't need to worry about the normal force or the perpendicular force. I'm just fighting the gravity, parallel component to gravity. So my net force is my parallel component of gravity. Notice I didn't know the mass of the CD. I didn't need to know that. Net force MA is mg sine theta. So the acceleration is g sine theta. So 9.8 times sine of 20 degrees. So the acceleration is 3.35 meters per second squared. Again, that acceleration is causing it to slow down. So if you want, you can call it a deceleration. And that's what we do when we put the negative sign here. To solve for delta t, v2 minus v1 over a. So it stops. So 0, the initial velocity is 4. So 0 minus 4 divided by negative 3.35. Okay, because it has to be a positive time. So delta t is 1.2 seconds. Okay, so this one didn't involve any friction. The third one's an interesting one. The fourth one you can try on your own about Batman. Everyone wants to be Batman, but I think there's something missing from that fourth one. So let's look at the third one. You have a skateboarder, maybe some of you are skateboarders, slides down a frictionless ramp inclined at an angle of 30 degrees to the horizontal. So my theta 1 is 30 degrees. The skateboarder then slides across a frictionless horizontal floor, so there's no change in speed, but then begins to slide up a second incline at an angle of 25 degrees. Okay? It's a fancy skateboard park, isn't it? So theta 2 is 25 degrees to the horizontal. The skateboarder starts at a distance of 10 meters from the bottom of the first incline. Now that wording is not so great. I mean, are we talking about the vertical distance or just walking down the ramp? I think it's just the ramp. Keeping on the ramp, it's 10 meters. How far up the second incline will the skateboarder go if the coefficient of kinetic friction on the second incline is 0.1? So there is friction on the second incline, but not on the first. So if I go here and I draw it out with my free body diagrams, question 3, so I have my normal force and mg cos theta, then I have mg sine theta. So again, the normal force and mg cos theta aren't important in the ramp on the left here. My net force is mg sine theta, so my acceleration is just g sine theta, right? We looked at that the very first example with the girl in the inner tube. So 9.8 times sine of 30 degrees. So 4.9 meters per second squared is the acceleration down the first ramp, which is frictionless. We can get our velocity at the bottom of the first ramp. v2 squared is v1 squared plus 2a delta d. So 0 squared plus 2 times 4.9, not 49, 4.9 times 10, right? So it's 9.9 meters per second. I'm not sure why this is here. Delta D. Is this just a check that the answer is right? 0 squared minus 9.9 squared over 2 times 9.8. Is that right? 9.9 squared divided by 2 times 9.8. I didn't put in the brackets. 9.9 squared divided by 19.6 is 5. Why do I have that there? Oh no, the acceleration is not 9.8. The acceleration is 4.9, right? So 9.9 squared divided by 9.8 is 10. So 10 meters going down. Then going up, the second. Okay, so here, my normal force is mg cos theta, and my net force is, well, there's no applied force anymore, so it's just friction and the parallel force of gravity, F of F and F parallel, which are opposing the motion. And so force of friction, we've shown before, is mu mg cos theta, because it's mu times F normal, but F normal is F perpendicular, which is mg cos theta. And so if you want to show off a bit, so the force of friction is that, and my net force then is ma, which is minus mg sine theta minus mu mg cos theta. Force parallel minus force friction. And you can factor out the mg if you want, punch it all in, and you get negative 5.03 meters per second squared. So then going up the ramp, it would be delta d v2 squared, 0 squared, because it stops, second ramp. Where does it stop? Minus 9.9 squared over 2 times minus 5.03. So 9.9 squared divided by 2 times 5.03, and you get 9.74 meters. And this is important information because you want to make sure that your ramp is long enough so you don't fall off the second ramp. That would not be a well-designed skateboard park, would it? Okay, so there's some other worksheets and things. So there will be some worksheets that will help with inclined planes, and that should be good. Okay, hope you are well inclined to do well. Hope you're so inclined to do well on these kinds of questions.